In this lesson, we are taking a look at compounding interest and a couple different ways that comes up along the way. We're going to start by looking specifically at annually compounding interest. So you're going to want to write this equation down, and then this formula is going to be used anytime we have compounding interest involved. Now that means that we have something that is repeatedly increasing or decreasing by a given percent every year. And it's every year in this case because this is annually compounding interest. But you might be wondering, what do all these letters mean in this particular formula? So here's a breakdown about what each of those numbers actually mean. So A represents the final amount. And remember when we write A parentheses T like this is function notation. So that actually means A of T, or in other words, the value of A at T. And T, you can see here, represents the number of years. P stands for principal. That is the starting amount. And R is the rate of change. And we always put the rate of change in as a decimal, not as a percent. So you see the example here, 5% would be written as 0.05. Make sure this is in your notes, and then continue on. We'll see some examples about how we use this formula. So here we're going to take a look at an example of something that can be modeled with compounding interest. So from 1990 to 2000, Microsoft stock increased by an average of 58.1% per year. That's outstandingly good. If you had invested $100 in Microsoft at the start of 1990, what was that stock worth 10 years later, knowing that information? And so we're going to use that same formula to be able to model this situation. So I'm going to start by writing down A of T here, and then that's going to equal, the first thing in our formula is the P value. P stands for principal, or the starting amount. Our starting value in this case is the 100. So since we start at 100, we're going to put that in first, so it's going to be 100 times 1 plus the rate, the R value. Now remember that rate needs to be written as a decimal, so we're going to take our 58.1% there, and we're going to divide that by 100 in order to turn it into a decimal. And so that's going to give us 0.581. And so that's what we're going to use here, 0.581 in the equation, and then that's to the power of T. Now in this particular problem, we actually do have a T value. And so I'm going to replace T with that. In this case, the T is 10. And so I'm going to put the 10 up here, but because I put the 10 there in for T, that means I also have to put it in here. And so remember that this 10 that's in the parentheses, that's just notation. What this is telling us over here is that we're finding the value of A at time 10. All right, so now that I have my formula, I can go ahead and now plug that into my calculator, figure out what value that will give me. When doing so, of course, use correct order of operations. So the very first thing you want to do is do the stuff inside the parentheses. So do the 1 plus the 0.581 first, and then the exponents will come next. So then you do that to the power of 10. And then the very last thing you do then is multiply the whole thing by 100. When you do that, you should be getting an answer here of 9,757.05. Now remember the context of this situation. This was actually money that had been invested and was growing by this rate each year. And so that means that $100 put into Microsoft at the start of 1990, 10 years later, became almost $10,000. That's a great investment. Of course, the hope would be that we'd be able to keep that going. So let's see what would happen here, because we knew what had happened from 1990 up to 2000. That's the data that we just used. But now we're going to make a prediction to see would it have kept doing that until 2010. So we're taking the same $100 that we started with in 1990, but this time we're going to leave it there for another 10 years. That means that our equation is going to be exactly the same starting amount, same rate, except for the T value. So the first time we had our money invested for a total of 10 years, this one's going in for another 10 years past that. So it's going to be a grand total of 20 years. So we're going to be using t equals 20 in this case. So again, go ahead and do that calculation, order of operations, parentheses first, then the exponent, then multiply by 100. Make sure you can get that correct number out. Be practicing this on your own. And we would end up getting then $952,000.99. That would be a great payout. I mean, put in $100 and have $1 million 20 years later. That's the power of compounding interest. When people talk about compounding interest, this is what it does for us, is it allows small values to grow up into very, very big values very quickly. The only thing, though, is this was a very, very exceptionally high rate of return in this case. 58% is basically unheard of. It does happen, as you see here, because yes, this is real data, but did it continue at that same rate until 2010? No. From the year 2000 to 2010, Microsoft stock actually decreased by an average of 6.1% per year. Okay, so let's go back to that original $100 investment we made in 1990. We found that that was worth $9,757.05 in 2000. So let's say we had taken that same amount and we just left it in there the next 10 years because we're hoping that it's going to continue going up. And so we don't realize that it's actually going to be going down by 6.1%. How would we write the equation to represent this situation and calculate that out? In this case, we're going to again start with our A of t value. So the amount after time t equals our starting amount. In this case, our starting amount is the $9,757.05 because we're looking to see what is it at from 2000 out to 2010. I don't want to use the 100 anymore because getting from the 100 to this number required a different rate than we're going to be using in this equation. And then from there, it's going to be times 1 plus the rate. And our rate here is 6.1%. And so I take my 6.1% and I again want to turn that into a decimal. So I'm going to divide it by 100. Anytime you want to turn a percent into a decimal, you divide it by 100. And that gives us 0.061. And so it's 1 plus 0.061 to the power of t. Although again, in this case, we're looking to see what it is in 10 years. And so instead of t, we're going to make that a 10. And because I put the 10 in there, I also need to put it in the function notation over here on the left-hand side as well. Now this equation is looking pretty good, except that it's not. There is one little problem with this equation, because right now, this would show that our value of our stock was increasing by 0.061 each year, by that 6.1%. But it wasn't increasing, remember, it's actually decreasing. So what that means is that when we go to write this, we still have all the same numbers in the same places, but instead of going up by 0.061 and therefore adding it, we are going to go down and therefore we are going to subtract it. Basically, it's kind of like saying that our R value is actually negative 6.1% instead of a positive 6.1%. And now that we have our expression here, we can go ahead and calculate this value out. Again, do the stuff inside the parentheses first, then your exponent, and then multiply. When you do that, you should get a value of $5,199.65. Now looking just at this one problem, this doesn't seem like a good thing. We started with almost $10,000 and we ended up with just over $5,000. You know, we almost lost half of our money. But this can happen in the stock market. All of these rates are seen as averages. Sometimes we go up more and sometimes we go down more. So this is actual real numbers. Okay, I want to remind you of that. These are the actual data based off the Microsoft stock values from 1990 up to 2010. Well, if I just look from 1990 to 2000, we got an outrageously good gain. From 2000 to 2010, we had a fairly decent decrease. But keep in mind, over 20 years, what happened is our original $100, yeah, it went down for the last 10 years, but it's still worth over $5,000. it still went up very significantly over that time. And so when people talk about investing, they always talk about invest for the long term. Just put it there and then don't worry about it. This is what they're talking about. They're talking about just put the money in and realize it will go up and it will go down, but on the long run, you should be getting some good returns. In these examples, I worked with the numbers in such a way that we were treating the growth of the stock as if it was compounding annually. But of course, stock is continually changing, and the compounding effect isn't necessarily just annually. In fact, interest can compound at all sorts of different intervals. So the next thing we're going to be looking at here is what happens when interest is not compounded annually. The equation is actually very similar to the one that you had written down earlier. This equation, you notice it has all the same elements in it, except it now also has a value of n included in it. This should also go into your notes. This is actually just a more generalized form of the same equation you wrote earlier, because this n value, that's the number of times that we are compounding the interest each year. That allows us to be able to compound the interest monthly, daily, quarterly, hourly, every second, all sorts of things that we can try and that we can actually have it compounding by. But how is this really the same thing? Well, in the case of annually compounding interest, we are compounding it once a year. And notice that if I plug 1 in for n, it's the exact same equation as what we saw earlier. So really it's the same thing. And therefore, of course, the A, P, R, and T all mean the same things that they did in that earlier equation as well. Once you have this down to your notes, then we're going to go and do an example together. All right, so here is our next problem. We take $1,000 and we place it in a savings account. Now, savings account generally, I hesitate to use the word invest there because it's not really a way to invest. It's just a place to keep your money so it's safe. But you can earn a little bit of interest in a savings account. 1.2% these days at least would be pretty darn good. But we're going to use that number mostly because it works out pretty nicely for this first example. In this case, our interest is being compounded monthly. That's fairly typical for a lot of savings accounts, where you get your interest paid to you and added into your account once a month. So we want to be able to figure out in this case, what will the value of our account be in 5 years? So after 5 years of $1,000 sitting in this account, growing by this 1.2% per year. Well, I'm going to go ahead and use that new equation that you just wrote down. And in this, a lot of it's fairly familiar, right? I know that A of t here represents the amount after t years, and in this case, it's going to be 5 years, right? So it's going to be P, that's our principal, 1,000, times 1 plus R. So R here is that 1.2%. But remember, I always want to turn that into a decimal, so I'm going to divide that by 100. That gives me 0.012. So I'm going to be using that in here, 0.012 over n. I'm going to come back to that in just a moment. And then that's to the power of n times t. And my t value here is 5 because we're leaving the money in there for 5 years. But the question is, what is the value of n here? Well, remember that n represents the number of times the money gets compounded per year. In this case, we're compounding monthly. Well, there's 12 months in the year. Therefore, this one is going to compound 12 times throughout the year. Notice what this equation is doing. It's taking our 1.2% that we get every year, and it's breaking that up into 12 little pieces. But because this is happening every month instead of just once a year, that means it's compounding more often during the 5 years as well. So it's actually going to compound 60 times instead of just 5 times. Now, between dividing it by 12 here and multiplying it by 12 here, what do you think? Are we going to end up with a bigger number or a smaller number than if we had just compounded once a year? Well, we're going to answer that question in just a moment. But first, we need to know, what does this actually give us? If we do that calculation, of course, do the exponent and then the multiplication, that gives us $1,061.80. So just sitting in the savings account by letting the bank hold on to it, you're able to turn your $1,000 into a bit over $1,000. Not a huge gain. It's better than nothing, but it's a very modest gain. Well, what if I took the same information and went back to the very first equation we did and compounded annually instead? If we had done it that way instead, we would have ended up with $1,061.46. So by compounding monthly, yes, we did end up getting more. Because you see, instead of 46 cents, we got 80 cents. We got a whole 34 cents extra. Now, that's not a whole lot in the case of the savings account, but it is more. And there's some interesting ideas about what happens if you compound more and more and more often. Could you get that amount to go up higher and higher? And when you start dealing with higher interest rates and higher returns, what kind of impact will that have? So we're going to continue looking at some of those types of questions and some of those ideas as we go forward. All right, so take a look at this problem. This is going to be the last one we do as part of this lesson. So I want you to see if you can do this one on your own first. Read through it, try working it through, pause the video here, and then we'll see how it's done together in a moment. All right, for this one, some things to leap out that I hope that you saw. First of all, notice that this is compounded daily. And so then I am going to be using that second equation that we learned about in this lesson. So it's going to be a of t. Now, do I know the t value here? Yes, the t value here is 20. So it's going to be a of 20 equals my p value, which in this case is 200, times 1 plus, and yes, it is plus because we're increasing. I'm going to take my 6% and turn it into a decimal. So 6 divided by 100, that's going to give me 0.06. Then that's going to be over the n value. And to find that n value, we use the fact that this is compounded daily. So we're going to have to put in how many days there are in the year. And we're going to go with a standard year, not a leap year or anything. So we're going to go with 365. And so that's our n there. And remember that n also appears in the exponent. And it's going to be multiplied by that t value, which remember we already found to be 20. From here, it's a matter of doing the calculations. So I want to simplify the part that's inside of the parentheses here. And when I do that, I get a big long decimal. Keep that decimal displayed on your calculator. Do not write it down and then round it. Otherwise, you'll end up with rounding error. Every little decimal makes a difference when doing something to this high of an exponent. And so if we actually do that calculation then, you should get $663.96.